Hello, this is Devin Garner, and I'm in group number 3 with Vanessa Cooper, working on the Go programming language. And this is a program we wrote for a loan amortization calculator. So basically, if someone has a loan with a bank for a house or a car, and they want to see a list of all of their payments and the amount of interest they're paying, then they would use this program to output that to the screen. So the input that's required is the initial loan amount, the date that the loan started, as well as 3 other terms where one of the 3 is optional. So the loan term in years or month, so for a house that typically would be 30 years or 360 months. The interest rate right now for a house is around 4%, and a monthly payment is all going to be dependent on the loan amount, but assuming a loan amount of $150,000, then the monthly payment might be around $600 a month. Because one of these is optional, if they only put in 2, it will automatically calculate the third based on the remaining 4 values. Okay, first let me show you how this program works so that you'll understand before I start explaining the code. So I'm going to run the loan amortization program, and I'm going to type in a loan amount. So I'll do 150,000, and I'll type in a start date. So I'll just use today's date, which is November 20th, 2014, and I'll choose to do yearly, and I'm going to do 30 years at 3.5%, and the last thing that it would ask me would be the monthly payment, but I don't want to figure out what that is because that would be a lot of work. So because I've entered both of these 2 optional parameters, then the monthly payment, which could be optional, because I've given a value to each of these, it actually will calculate it on its own. So after I hit enter, then it outputs my chart. So here is 1 year at a time, the amount of interest I paid that year. So you'll notice there's a lot of interest in the beginning, very little interest in the end. The amount of principal that I paid off each year in the beginning is going to be quite low, and the end is going to be quite high. And the balance will slowly reduce until I paid the thing in full. So my total principal that I paid was 150,000. However, my total payments is much higher than that because I had so much interest. So I didn't pay quite double, but I paid an extra 80,000 because I did 30 years at 3.5% interest. So loans can be quite expensive when you look at the true value that you've paid. Okay, so let me dive into the code. I'm going to skip over some of the syntax of Go because the previous videos that Vanessa did with PowerPoint slides explains a lot of this, but I'll just go over the key parts of the program as well as some syntax that we haven't gone over yet. So the packages that we're importing from the standard Go libraries are math, which I'm going to use exponents from that, format for printing to the screen, buff.io for creating array type buffers, which will be related to the console input, OS, which allows me to access the console input, strconv, which allows me to parse strings to integers or floating point values, strings, which allows me to do comparison between strings, and time, which allows me to do date and time manipulations. So in my main function, I have 2 main sections. One is for doing all the input, asking the user for the values needed, and that goes down to about here. And then the second section, I calculate the omitted value between those 3. And the last is I call a function to output everything to the screen. And I'll go over those methods in a bit. So starting at the data input. Okay, so I'm going to start with a variable that can read from the console input. standard in is the console input stream, and buffio.new reader will allow me to access that. Each value that I'm asking the user to input, I've coded surrounded by an infinite for loop, so there's no condition. The reason for that is they might type an incorrect format, and if I can't parse it correctly, I'm going to ask them to repeat typing the value until I'm able to parse it correctly. So to get the loan amount, I first prompt the user, and next I'm going to read from the console input buffer into this variable, loan amount of string. Now this is an interesting concept that we haven't discussed previously, is that a function can return more than one value, which is kind of interesting. So in order to do it, you need to assign each value to a different variable, and on the left hand side of the equal sign you're just going to comma separate each variable. And in this case, I don't care about the extra value that's returned from read string, so I just use an underscore, which basically says ignore this variable. So after I read in the loan amount as a string, I'm going to parse it with this string conversion.parseFloat. First, I'm going to remove any $signs or commas with the string replace method. And on this one, it also returns an extra value of a type of error. And I've never encountered any errors with the read string from the console input. I ignored the variable by labeling it an underscore. But the parse float, I do care about the error, because if they type in a letter, I can't parse that into a floating point value, and so I'm going to need them to re-enter the value. So if the error is nil, then that means I can quit out of the for loop. But if there is an error, then I need to tell them they've typed an invalid value and they need to re-enter it. So the other values that I ask the user for follow very similar code with an infinite for loop and some reading from the console, a prompt, as well as a parse. But I'll just go over the slight differences in each. This one I'm using time.parse, and it's to get the starting date of the loan. Time parse requires you to pass in a format that you want it to be read in, because I could choose to have them type in JAN for January space 02 space 2006, or write out the full month January instead of JAN, but I want them to just do the standard date format with slashes. And the way that this format works is there's an exact timestamp value that you have to pass in, which is January 2nd at 3 hours, 4 minutes, and 5 seconds p.m. with in 2006 with a time zone of 700 hours from GMT. The reason is, if there's an exact timestamp that's passed into the format, then Go is able to figure out, based on the numbers you passed in, which number corresponds to which piece of time. And so you're able to create any format you want, and it'll output or parse using that format. So it's actually a pretty clever way of doing parsing. For doing the yearly, the only difference is I'm using strings.equalFold to compare what their input was to the Y or M character. The reason is equalFold is a case insensitive comparison, so they could type a capital Y or a lowercase y and it would be the same. For term and months, one thing I do differently compared to the previous is I allow it to be optional. So after they input, if they input an empty string, then I quit out which would mean they chose to have it be optional by just hitting enter. The other thing is parse int I'm using to convert it from a string to an integer. The obvious parameter is term as string, which is the value they entered, but it has two additional parameters which are not so obvious. The first is the base. So 10 is our normal 10-digit system, but you could put in here a 16 for hex, or an 8 for octal, or a 2 for binary, and it'll parse any of those formats. And the last value, the 0, tells it how many bits to use for the int variable data type. So options would be 64 or 32. And I chose to do 0, which means pick whatever's best for the particular processor that I'm on. But in this case, since my variable itself is int64, it doesn't really matter that I told it to pick whatever it wanted, because it's going to typecast it when it puts into the variable anyways. So the other thing I do differently is based on whether they put in year or month previously, I want my values to still be consistent in either mode, and so my variable is term in months. So if they happen to be in yearly, I'm going to times it by 12, so I'm basically going to pretend that they put in a month value instead of a year value, so that all my calculations can be consistent. The next, for APR, the main difference is that because I'm only able to have one optional parameter, then I check whether or not term in months was entered previously to determine if I want APR to be optional or not. So again, with the empty string that was input, I allow them to quit out as optional, but only if they actually put in a term in months value. Otherwise, it's not optional. I'm going to require them to type a value. And the other thing I'm doing differently with APR is I'm removing the % sign with string replace if it's there. And also, if it is there, I'm going to divide the APR they entered by 100. So if they put in 3.5%, I'm going to change it to 0.035. For the last term, which is a monthly payment, if they've already entered both the APR and term in months, then I skip over this input altogether, because that means this last one can be optional. However, if they haven't put one in for each of those, I'm going to require it. And it's very similar to previous examples. And I'm going to remove the $sign and the comma when I parse. That way they are allowed to type it in as currency, but when I parse it to a float, then it will be a normal decimal value. Finally, after I have all the input, I need to calculate the optional value that they chose not to enter. So I have three different methods for that: calculate term in months, APR, and monthly payment. So whenever one happens to be empty, I'll call that method and pass in all the other values, and it'll return the value that's missing. And I'll go over those methods in a minute. And the final is outputting the actual chart. I pass in all the values, and it'll loop through and output everything to the screen. So to output it to the screen, first I output to the console a header for each value and a few tabs to separate it to make it look like a chart or tabular format. Also, I have a payment and a percentage rate variable which will be consistent whether it's yearly or monthly. So if it's yearly, I'm going to take the monthly payment and times it by 12. If it's monthly, I'm going to take the APR, which is an annual rate, and divide it by 12 to get the monthly interest rate. And then I'm going to take the initial loan amount and put it into the balance. I'm going to have a loop over the balance that as long as the balance is greater than 0, it keeps looping. And I'm going to iterate over each payment and subtract the payment from the balance as well as add the interest to the balance until the balance becomes 0, and each time I'm going to print out the result of the payment. So to do that, first, if the payment is greater than the balance, which will only happen on the very last payment, then I'm going to modify the payment to be equal to the balance. That way they don't pay the bank too much and cause their account to actually go negative. Next, I'm going to calculate the date. So this add date function has three parameters. The first is year, next month, and last is day. So here, if it's yearly, I'm adding 1 year to the previous date, and if it's monthly, I'm adding 1 month to the previous date. Next, I'm going to subtract the payment from the balance, and I keep an aggregate total of the payments, principal, and interest. So they all three start at 0, but I'm just going to add the payment to that total, and that allows me to do a summary at the very bottom that says what the total was for each of those. Next, I calculate the interest by timesing the percentage rate by the balance, and the principal, which is how much the balance will actually be reduced by, is the payment minus the interest. And even though I reduced the balance by the full payment earlier, I'm going to add in the interest afterwards. So in the beginning of the loan, the principal will be quite low because the majority of the payment will be interest. And towards the end of the loan, the end of the 30 years, the principal will be much higher and the interest will be much lower because the balance will be lower at that point. So finally, I'm going to output the interest, principal, and balance, which will go underneath the headers that I've placed here. The printf has special syntax which specifies how something should be formatted as it's going to the console. So %v simply means to output whatever the value is straight across, and each percent will correspond to a parameter that's being passed in, and so I can pass in as many parameters to this function as I'd like. The %.2f says to take a floating point value and truncate it to only 2 decimal places when it's printed out. The reason for that is because I'm using a floating point system that is based on a certain number of bits, then the precision is not perfect. So there's a chance that all these calculations might cause a decimal place to be in more decimals than just 2. But with currency in the US, we know that the smallest we can get is a penny, which is second decimal place. So if, because of a precision error with the floating point system, if I happen to get into a third decimal place or higher, then I'm going to truncate it to 2 decimals so that the user's not confused. And then finally, I'm going to output the sum totals. Next, I have these functions which calculate the missing values. So for calculate monthly payment, I just found a formula online which could calculate that. So the main thing that's interesting here is the math.pow, which does an exponent. So it'll take this value here and raise it to this power. Otherwise, it's just a simple math formula. The calculate APR is actually quite complicated because with compound interest, you can't use an algebraic formula to figure out what the percentage rate should be. You possibly could do it with calculus or something, but there's no simple algebraic formula. With simple interest, there is. So what I actually do is I use the formula for simple interest here, and I put that into a possible APR value, and I have an infinite loop here which essentially does trial and error, and it modifies this possible APR by adding or subtracting. Well, it starts with 0.1%, and then it'll move on to 0.05, and then it'll move on to 0.005, and it'll keep getting more and more precise until it finds the correct APR. So the way it's able to do that is if we assume that that's the correct APR, we can call calculate monthly payment on it and check if that fake monthly payment is equivalent to the monthly payment that the user input. And as soon as it is, we know we found the correct APR. And one extra thing I'm doing is I'm truncating to 2 decimal places, essentially rounding it for the monthly payment, because and I do that by timesing by 100 and dividing by 100, and after I times by 100 I truncate it by casting it to an integer. So it's probably not necessary to do that on the user input value because they'll type it in correct currency, but because I'm using a made up APR, that monthly payment needs to be truncated to 2 decimal places, otherwise it may not match with the user input. And as I try to get closer to the correct APR, then I'll check if I get into a flip-flop scenario where the last time I subtracted 0.5 and this time, and it was wrong, and so now I'm adding, or it was too low, and so now I'm adding 0.5, and now it's too high, so I'm in a flip-flop scenario. In that case, I'll, instead of using 0.5, I'll switch to 0.005 by basically dividing by 2, or timesing by 0.5. So that's a little tricky way to calculate the APR, but it seems to work. And that's what was suggested online by mathematic blogs. So calculate term in months, the way I do that is basically the same as this output chart where I loop over the whole balance, but I do much simpler calculations and I don't do any output. So I take the balance and or the initial loan amount, and I loop over by subtracting the monthly payment and adding in the interest, and I just count how many iterations of the loop it takes to finish, and then I return the value.